I'm trite, and it's really not.
That's trite.
Really hard to believe sometimes. Trite? No, that's triste. No trite. Do you guys know what trite means?
No.
It's kind of like not redundant. Flippant, off the cuff, just kind of like a yeah, it's true, whatever. It's trite. I don't have an example off the top of my head for trite, but yeah, like a statement that you say and you don't necessarily really mean, or it doesn't have a lot of weight to it. Does that make sense? So some people are like, oh yeah, God is good, and you're like, oh no, like I don't believe God is good half the time, because when hard things happen, I'm like, where is he? Why is he? Does he love me?
So when people are like, I'm starved, or like, I'm dead, they're not actually starved.
Actually do start.
That's kind of like a hyperbole, though.
I'm dead.
I don't know. There's another phrase for it besides trite, but it's not English class. What are we doing? Math. Okay, here we go. All the math teachers use good English. English teachers should have good math, but that's okay. In number 121.
Answer B.
How did you do it?
Plug it in.
Plug it in.
That's what you're always supposed to try, even in all of these ones, right? But coming back here, yes, if you plug it in, you should have ended up with what in the numerator?
Wait, what?
2.
No, what are we asking?
Isn't that a negative one?
No.
Because 8 times 2 is, because it's 16, and 16 minus 5, or 25 is negative 9.
Yes.
What's in the numerator?
2.
3, sorry.
So then your final answer would end up being?
Negative
Okay.
1.
I got that.
Because it's 4 and 8, and 8 minus 6 is 2, and 2 plus 1 is 3. Okay. Number 122, what made it a little bit harder?
The whole thing.
3.
Because those were keep goings, right?
Yes, but don't know how to keep going.
And then the piecewise dude. The piecewise dude, don't I have to come towards 2 from both directions?
Yeah.
Because, am I looking for the at, or am I looking for the approach?
The approach.
Ah.
The
Okay, so we have to struggle through these ones a little bit. Let's come back to number 122. I'm going to take him to the separate page. We're going to walk through one by one. But how many of you guys think the answer is A? How many of you guys think the answer is B? C? D?
It's either B or D.
So most of you didn't answer. What happened to your educated guess? If it's a multiple choice question, you educated guess. So stop.
Right.
Just pick a letter in your head that looks right, that feels right. I don't know. What else am I supposed to say at this point? You have like 5 minutes to work on 10 minutes to work on it? A long time. How many of you guys think it's A? Just raise your hand. You're picking it. B. Lock it in.
Yeah.
You just did it because they did it. C? Okay. D. All right. I think almost everyone voted. We don't think it's A, so hopefully it's one of the other ones. Number 123, though. What's going on with this guy?
Well, thank you so much for
You
that.
plugged in, right?
Yeah.
Keep going.
How do you keep going on 123?
X squared minus 9, x squared plus 9.
Ooh, look at you guys doing some difference of squares factoring.
Okay, Kyle. X minus 3, x plus 3.
Should have kept going because that's the difference of squares. I
You're not
like
ready
it.
to learn it?
I like it a lot.
Yeah.
Technically, we're still writing the limit because the limit's not done yet, right? Okay, what do we get to do?
Reduce.
Reduce. And when we reduce, what do we try to do?
Reuse the
Plug it in.
Funny.
So we end up with equals, because now we're plugging in and we have it. 3 plus 3 is 6, and 3 squared is 9 plus 9 is 18, and 6 times 18 ends up being?
108.
108, because we can do 2-column multiplication if we can't do mental math.
Wow.
I was thinking multitasking.
Like multilingual.
Sure.
Yes.
So now we have number 122 that we need to figure out. True?
Yes, ma'am.
So what's the first one that we're supposed to be checking?
Limit.
As
X approaches 1.
of
X cubed plus 1.
cool. What's the second one that we're supposed to be checking?
As x approaches limit as x approaches 0. Absolute value of x over x.
What's the third one that we're supposed to be checking?
Limit as x approaches 2. F of x, where f of x equals 3.
Keep going. 3 what?
Greater. Yeah, why am I doing saying this?
No, there's a function though, isn't it?
Yeah. No, it's 3, 0.
Oh, it is 3. Okay.
Yeah.
Such that
X less than 2.
So this guy, we plugged in, we got 0 over 0, keep going. Factor, it's easy. Why isn't it easy?
And it's X cubed.
You guys just did a 4th degree polynomial. You just did x to the 4th minus 81 over, whoa, if you can do that, what makes this one so much harder? It's a cube, it's not a difference of squares. In your notes, can you guys check really quickly where we first started talking about 0 over 0, keep going? What was the first keep going way? I know it was factoring, but there were a comma, 2 other things that you could try.
This started 1.4, 1.3.
We're talking about 1.3. We talked about 0 over 0. We talked about 0 over 0.
Oh,
synthetic or long division?
Synthetic
So
division.
factoring is one way, but synthetic or long division is another way. Now, quick reminder from freakout. Quick reminder from freakout as I separate my work to make it nice and neat, because I asked you guys to be nice and neat. So, there's arrows. Oh, that wasn't straight. I like that.
Whoa, that's so cool.
That's not straight.
All right, hold on. So much judgment. You try it. Okay, so no, you want this. When are you allowed to do synthetic division?
If it's an X minus.
If it's an X minus or an X plus, I have to have like a little linear pair is what we would call it last year. Is this a linear pair?
Yes.
Yes. You think it will always be a linear pair?
No.
Yes.
You hope yes.
Yes, I hope
But the true answer is
Reality says
No.
it
No.
is.
So if you guys were doing synthetic, you would throw the 0 or 1, x minus 1 equals 0, but x equals 1, in the box, and then you would throw in the coefficients. Why am I doing 1, 0, 0, 1?
You still need the X squared and the X.
1 x cubed plus 0 x squared plus 0 x plus 1. Okay. And we would do synthetic division where you bring down and then you have the 1 and then you carry the 1 and then you bring down and then you, wait a minute. What's wrong? What am I supposed to be doing?
Add. Subtract.
Whoa.
Wait. Oh.
What am I?
Whoa, it's whoa with me.
Wait, why
Wait
is
a
it?
minute.
Why is it negative?
It's just subtracting.
Oh, you're right.
Yes,
It's
ma'am.
division, so we're subtracting, right? So you bring down the 1, because it's division. You bring down the 1, and then 1 times 1 is 1, and 0 minus 1 is negative 1, and 1 times negative 1 is negative 1, which is negative 1, and negative 1, which is 0.
Your hole.
0.
What does that mean? I can replace this with the limit as x approaches 1 of x squared minus x minus 1. Now for some of you, synthetic division is a great shortcut, but there's way too much shortcutting happening, and you've lost all understanding of what the crud we just did. So can I show you long division real fast?
Sure. Why not?
So I'm going to do a little or. That's synthetic division, it gets us here. What we're truly doing is we're dividing the top by the bottom, which long division we can do whether or not we have a linear pair. We can always divide the top by the bottom, whoever the bottom is. We can ask ourselves, x goes into x cubed how many times? I'm going to change colors because it's going to get messy.
3.
3 times x is 3x.
X squared.
X squared times x is x cubed. Good. So then I have x squared minus x cubed minus x squared. It's division, so we subtract. Do you see why we're subtracting? Those are going to cancel. What's 0x squared minus negative x squared? 1x squared. With that negative times a negative, which is a positive. Then I have my 0x and I have my 1. How many times does x go into x squared?
X.
1 time, right?
Mm-hmm.
And then I have x squared minus x, the little subtraction. Then I can cancel, and that's going to be a positive x. That's this one. Plus 1.
It's wrong.
Wait, going to the yeah, it's the
Could do 1. And x minus 1. What do you guys see? It's going to be 2. So what's wrong? Why was my synthetic division wrong? And why did I take all the time to show you long division where you don't lose understanding? what did we do up here in long division? What did you guys do? Blindly follow me as I twisted around synthetic division to make it work. I twisted around synthetic division to make it work. I wanted a remainder of 0 because then everything is nice and pretty and neat, and I can take it away and I can factor it out. But was it nice and pretty and neat? Did it go in perfectly as we divided? No. So how does synthetic division actually work? Now, a few of you guys are trying to argue, but most of you blindly follow.
You add, right?
Synthetic division. Do you use it with the sign as is, or do you flip the sign when you put it in the box?
You use as is.
Well, if you're doing long division, you use as is and you do subtraction along the way. Usually when you learn synthetic division, you use the 0 instead, which was the positive 1. But since you flip the sign, you don't subtract like you do in long division, you actually add. Which a few of you guys were trying, but it wasn't going to work. The remainder wasn't going to be 0. And I know enough math students that if it's not working, you're like, I'll just tweak it. Maybe I'm wrong. Okay, no. So what was it supposed to be? 1, 1, 1, 1, 1, 1, 2. So is this right?
No.
No. So if we were to rewrite the limit, we would get the limit as x approaches 1 of x squared plus x plus 1, remainder 2, which would be 2 over x minus 1. Question, did dividing get rid of my problem?
No. Made it
Why?
worse. There's still a fraction.
I can plug it. What was wrong from the very beginning of us looking at number 1? It was a number over 0, not a 0.
You tricked it. We bluntly followed you again.
Oh no!
You're so evil.
So why don't you guys stop me? Why don't you correct me? You have to speak up if you disagree.
Always right.
I know, which is what I need you to realize, that either A, I'm not, or B, I'm trying to become, or B, like you guys on a test, and you're like, this doesn't feel right, I'll just do something else and hope it works. You have to have confidently down the process. So what happens when you plug in 1?
It's 2 over 0.
It's 2 over 0. What does that mean? Not keep going, but
Infinity.
plus or minus infinity. Good. Check the signs. Let's come back to our works. But the nice thing is, guys, even if you had done this whole, now, let's be honest, you wouldn't have been able to factor that, most of you, right? You would have needed to do some sort of synthetic, I don't know, something addition. Division, sorry. So it was good that we reviewed this, because sometimes it's necessary, sometimes it's good, but if you did go to plug in, wouldn't you still get a number over 0? So either way, we have a number over 0, we're doing plus or minus infinity, checking the sign. I think it'd be way easier to do it up there than down here. So let's come towards 1 from below. Let's just say f of x to be lazy. And let's come towards 1 from above. Has anybody already done this? What happens if you plug in 1.1? Cube it and add 1. Positive. What happens if you plug in 1.1? Sorry, I'm doing the above. And you subtract 1. Positive. So this one's going to be what kind of infinity if it's a positive over a positive? Positive infinity. We're just checking this one. What happens if we do 0.9? Cube it plus 1. Positive, but 0.9 minus 1. Negative.
It's no existo, limit existo.
Negative infinity. Therefore, that limit does not exactly. So, do we already have a D on E1?
Yes.
Yes.
So B is not right. No. So D wasn't either.
So yeah, well no, that's a good strategy. We've only done 1 out of the 3, and maybe we can narrow down to make our
There's no A or C.
chances better. So it's not none, because this one does not exist, right?
Boy.
Which one else? Which other one? Oh, C doesn't have 1. So it's either B or D.
No.
Yeah.
It's either A or C.
B or
It's
D.
either B. Which of the following limits? Ah, now careful. They can ask it either way.
Oh, wow.
They can ask it either way. You have to pay attention to the wording. And some of you guys, they could ask, which of the following are false? Which of the following are true? Which of the following are always true? Which of the following could be false? Like, it gets rough. Just be careful. it gets rough. Coming back, so it's either B or D. Can you guys be strategic for a second?
Do D. Number 3.
If it's B or D, what should we check next? Number 2 or number
Number
3?
3.
They both have 2.
Never mind.
They both have 2. Now, you guys should understand why 2 is true, but let's go to number 3 and then we can make the match and that would save time, right?
Yes.
So number 3 is that piecewise dude. So that piecewise dude, we have him over here. How to take the limit of the piecewise? Oh, no big deal. Plug it in, plug it in. Where's the at? Wait, that's so wrong. Because we don't care about the at, we care about the approach. And the approach has 2 sides.
Oh.
Because if you come towards 2 from below, and if you come towards 2 from above in a piecewise, you're plugging into 2 different pieces. Now this one's nice because there's no x to actually plug in. We just get to look at the numbers that are there. But guys, 1.9 would be which piece? The top piece or the bottom piece? Yeah, because 1.9 is less than or equal to 2. So if I was coming from below, all of them are having heights or function values of 3. But if you come from above, 2.1, 2.01, 2.001, aren't all of them greater than 2? So what's going on from that side? 0. It's going to those weird graphs where we have coming from below everything and equal to, and then coming from above everything or every time you guys saw a weird graph with different pieces, it looked like or similar to this type of function, a piecewise function. Ooh. The point exists, the at exists, but forget the at. What's going on from either side? Agreement? No. The limit does not exist.
So it's D. We were all wrong.
Well, a couple people.
So
guessed
it is
D.
B?
It's D.
So 1 doesn't exist, 3 doesn't exist, so therefore the right answer is D, because that's the only one that has 1 and 3 not existing. 2 does not exist also, so those of you guys that chose B, you're right that this did not exist, but did you know why?
What is it?
Do you guys know that the absolute value of x behaves differently depending on whether x is a positive or x is a negative? You guys know that positive numbers stay the same and negative numbers flip their sign?
Yeah.
So then technically we could do the limit as x goes to 0 from below and the limit as x goes to 0 from above. And from below, I would have to do the less than 0, the negative x option. So I could say, oh, hey, that's the same thing as looking at not the absolute value, but the negative, the opposite of those values. I'm using that piece all over x. Isn't that negative? And from above, I can use the positive portion of that piecewise function definition of absolute value. Because from above, it would be this piece, which is positive 1. Do they agree?
No.
Nope, the limit does not exist. DNE because they do not agree. DNE because they do not agree. DNE because, well, A, they were infinities, but then B, they do not agree.
So, DNA.
Okay, so here we go. Section 1.4. Get back to your notes. Get back to section 1.4. We need to talk about continuity and one-sided limits. For about 20 minutes. A little bit less. Maybe 15. Continuity and one-sided limits. Do you guys notice how we had some nastier limits right there? Yeah. And almost all of them involve piecewise functions or number over 0. We're going to take some notes on piecewise function limits probably another day. Not today because we're going to run out of time. But Tuesday, we should get back to our flip book. To the very back reading the piecewise function. That might be good to look at. But for today, we at least saw it in an example. Here we go, continuity and one-sided limits. Yesterday, we talked about, because you guys took some time to write this all down, we talked about, or at least we're trying to discuss, what is similar, or what is the same with all 4 of these graphs. I'll tell you what's the same. All of them are discontinuous at x equals c. but the reasons vary. All of them are discontinuous at x equals c, but the reasons vary. So we have to figure out what discontinuous means. If they all are discontinuous in different ways, well, how do we have one definition that encapsulates it all? That would defend all four discontinuities. So, first of all, what makes the first one discontinuous? The function doesn't exist. The function doesn't exist. So if the function doesn't exist, if there is no point somewhere, well, you'd have to pick up your pencil when drawing it, technically, right? Now, would the graphing calculator show that? No, because the pixels and that, technically a hole has absolutely no space. It's like an infinitesimally thin, a dimensionless missing point. Because the point, and the point 0.001, like they squish in so close that you can't actually see the instant when it's gone. But that's okay. Either way, the function doesn't exist, but your graphing calculator is like, Okay, why is this one discontinuous? There's a point. Look, it's good. FFC exists.
I agree.
But it's broken, and the way that we describe the brokenness is with a limit not existing. I could apply this to life if I was really nerdy. Okay, so the brokenness can be described by the limit not existing. Brokenness can be described by a limit not existing. So in this one, the limit didn't exist. The point was fine, the limit was not. This one, why is it discontinuous? The limit exists, the point exists.
But it's a massive thing.
Don't you have to pick up your pencil to go over and ask myself no matter what? So even though this is a piecewise function where they had this guy, the 1 over x squared, that had been like shifted, they also have for x equal to c, for x not equal to c, like 1 over x squared shifted. For x equal to c, they have a point. This infinite limit, even though we would write positive infinity, by writing positive infinity, we're admitting a vertical asymptote, which means there's a discontinuity. Even though FFC exists, even though the limit agrees, that infinite limit is like, nope, discontinuous. Another way of looking at it is actually the reason why number 4, why this one's discontinuous, we can kind of use it for this one too. Why is this one discontinuous? There's a point, yay, there's a limit, yay, so what's wrong? The graph agrees. The approach agrees. The at is there. But what's true about the at and the approach?
They don't
agree. So if the limit and if the point don't agree, that is also a discontinuity. There's going to be a jump. But not like a broken graph jump, just a single point jump. So it's not existing in a different way. This one, the limit doesn't exist. This one, the discontinuity is there, even though the approach is good, the point is good. So we can come back here and say, okay, technically where the limit was going and where the point was, those weren't in agreement, so we could say that's the reason why this guy is discontinuous. And this brings us to what we have to use as the function of continuous. It has to be kind of complicated because there are lots of different ways a function can be discontinuous. We just kind of looked at all the different ways. Oh, my order just disappeared. We just basically looked at all the different ways that a function can be discontinuous. And so, all right, that didn't work. We'll just leave it there. We have to have all these different ways. All 3 of these things have to be true in order for a function to be continuous. The point has to be there. If you are a visual person where the math terminology gets confusing, if I were you, I would kind of write off to the side, maybe in some sort of light colored pen or pencil, what this really means. So if f of c is defined, the point or the at exists. Now guys, you wouldn't have to put this on a forever quiz, but this is making sense of it in your brain, yeah? So if f of c is defined, the point or where it's at exists. It's filled in. There is a location. This one, now technically, hold on, I'm missing stuff, right? Shouldn't I have, but my processor wasn't letting me. We need to write down the limit as x approaches c. because we're talking about at C and around C. The limit as f of x exists, we can say the approach exists, right? And even better than the approach existing, can't we say the approach agrees? The two different approaches agree. AKA, the function can't be broken at a point. The function can't be broken as in the paths. The approach, and if that's grammatically kind of annoying to you, you can say the approaches. You're talking about both approaches, from below and from above. The approaches agree. And then this one ultimately is saying the at and the approach. I'm going to say the approaches agree. So there's a lot of different things that can go wrong. The point could not even be there. The approach, the path could be broken. Or the approach and the point could not agree. So here's one way of writing it, kind of in one nice short sweet statement. And this one we're going to go ahead and make an official. Those are unofficial parts of the forever card just to make sense of it in your brain. But we can also say something to the effect of, okay, the point has to exist and it has to agree with the two one-sided limits. The point has to exist and it needs to agree with both of the one-sided limits. If there is a DNE or a not equal in any part of this statement, then the function is discontinuous. So either the point doesn't exist. If there's a DNE here, okay, forget it, discontinuous. Or if there's a DNE here, like this is a not equal to, because they don't agree, okay, fine. The function is not continuous. Or if there's a not equal to here, where those or these don't agree, then the function is discontinuous. Note if any of the above conditions fail, the function has a discontinuity at x equals c, which could be like a vertical asymptote, it could be like a hole, it could be like a broken graph. Let me do this and let me do this. I'm putting a yellow box around all of this. What does that mean?
Forever.
This is forever number 4. Forever number 4. Definition of continuous can be the title of the card. Definition of continuous can be the title of the card. Forever number 4. Definition of continuous can be the title. Huh? Say it one more time.
Quiz on the night.
Oh, the forever quiz. Yep, it's coming. Forever quizzes are usually the day before a test or 2 days before a test, depending on how everything turns out.
Are those just exactly like the forever cards, or is it like problems based on?
No. Good question. As you guys now have 4 different forever cards, and you're thinking of maybe like, oh, I should be writing these down and studying them. A forever quiz, especially on this one, could be something like sketch the basic graph of e to the x. Shoot, there it is. Give the function for the basic graph of something that looks like starting in the middle, like this. Oh, it's a sine curve. Sine of x. It could be something like state the entire definition of continuous.
Oh.
So it could either be a piece of a card or it could be an entire card. It could be a fill in the blank of a card, but that usually isn't. You could do a function is continuous at x equals c if the following is satisfied. So you could do 1, 2, 3, or you could do this entire statement with these words. Or you could do the whole thing and be amazing. Who wants to be amazing?
Nobody.
Oh, party pooper. Okay, hold on. I have piecewise-y stuff. But piecewise-y stuff I said we might leave until another day. It's kind of like an aside, so let me go ahead and put that before section 1.4. And let's skip to our discontinuities. Remember how I said there are different types? This is kind of like a freak-out review right now. Removable. If a function has a removable discontinuity, we're going to say either f of c does not exist or f of c does not equal the limit as x approaches c of f of x. If we want to talk about it in terms of the definition, either f of c doesn't exist, which would be this one, or f of c does not equal the limit as x approaches c of f of x. And those are the two pictorial examples of how that might be true. Non-removable, I want you guys to ponder the different ways that you see the function might have non-removable discontinuities. Now up above, we can kind of say removable ones involve holes, which we've seen before, right? Holes are non-removable, are removable discontinuities, because algebraically we can reduce, and that would be our 0 over 0. We can reduce out the problem if it's like a simple algebraic one. But another way of saying removable is something to the effect of redefining one point fixes the problem. Maybe I should say repairs the problem, but that's okay, not being super grammatically correct. Fixes the problem. All I have to do is fix one point. All I have to do is either fill the hole or I need to redefine a point. Basically, I'm filling the hole. So redefining one point will fix a removable discontinuity, but non-removable, there has to be a lot more work that's done. We have to actually translate an entire function if we were trying to make these two pieces match. Or maybe it's like this crazy sine of 1 over x thing where we can't fix it. There is no fixing. The oscillations make it so this part. Give it back to you. But non-removable can be either a vertical asymptote for putting in the names. I forgot where I put everything. Apologies if these are defined two different ways. That should have gone there, that should have gone there, but that's okay. We have a jump, which can also be known as a break, or we have oscillations, like the crazy.
1 over sin of it?
Yeah. Careful. Sine of 1 over x. It's a little bit worse. There we go. Or we have a piecewise function, where we have two pieces that are not matching up for x below c and x above c, and the below has the or equal to in this one. Or we have the vertical asymptotes. And technically, guys, I need you to know that even if there's a vertical asymptote, that function is discontinuous. I know the limit is infinity, but because the limit is infinity, getting closer, 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 there is a vertical asymptote, which you should remember is a discontinuity. So we can make this like 1 over x minus c squared. It has been shifted to the right. So oscillations, jump or jump break. Jumps or breaks. The function itself, the vertical asymptotes. And if you're thinking about the definition, this would be something where the limit does not exist. This one is where the limit does not exist. And technically, this is where the limit does not exist. It's infinite. So if you notice, removable discontinuities have to do with point problems, and non-removable discontinuities have to do with limit problems. You kind of want it like a category of separating the two. Removable discontinuities have to do with point problems. Non-removable discontinuities have to do with limit problems. So one example would be number over 0 or piecewise issues. Piecewise issues. Ooh, hi.
Good morning.
Yeah, just wanted to, be a part of class. So what if, bloop, bloop, bloop.
Oh boy.
What if you see some polynomials and I ask you about the continuity of polynomials? Wait, polynomials. What's the domain of polynomials? Discontinuities are seen by limited domains. All real numbers. So guess what? Polynomials are continuous for, can I do snazzy R? Mr. Che, what is
Yeah,
that?
Mr. Che.
Continuous for all real numbers. Exponential functions. Oh, this is hard. Wait. Doesn't e to the x go forever left and forever right?
Yeah.
Oh, hey. That guy's continuous for all real numbers. Wait a minute, hold on. What category is this? Common functions, continuous for all real numbers. Oh, they all are. Polynomials are good everywhere. Exponentials are good everywhere. Absolute values are good everywhere. Sine and cosine, good everywhere because it goes forever left, forever right. All their domains are all real numbers. Cube root, fifth root, tangent inverse, good for all real numbers. Why? Because all of their domains are all real numbers. So these ones are all good. So who's not good? You know everybody else. But only at certain points, only at certain places. So there are properties that we can talk about as far as continuity. If you have a continuous function, then if you multiply a continuous function by some sort of constant or some sort of scalar, guess what? It's still continuous. If you add a continuous plus another continuous, like sine plus e to the x, guess what? It's still continuous. If you multiply something like an x squared times a sine of x, no big deal, still continuous. And if you divide a continuous, like x squared all over another continuous, e to the x, it's still continuous as long as, I just made a denominator. What do I have to watch out for?
Zero.
Okay, so division, it's always going to be continuous as long as the bottom's up. Bottom 0, then we got some issues. The bottom 0, then we have some issues. Why are people walking around in classes? Good question.
They're walking back to class. Class sometimes goes out. I think it's both usually both or something.
Because they run a project.
With each other.
Alright guys, here's the dealio. We've done a great job today of getting a lot done. The only dilemma is we didn't get near enough done. You know what that means?
Pushing it to Wednesday.
Yeah, we're pushing it to Wednesday.
Oh.
I know. Same.
Ooh, what about test corrections?
Wait, where are test corrections?
Good question. So, homework this weekend? It's not gonna, well, you can start. You can start, but we didn't get to talk about, hey, like, you know, talking about continuity and talking about piecewises and law to depth, etc. So this homework is now going to be due on Wednesday. So what is the weekend's homework if this is not due until Wednesday? Test corrections, aka the summer quiz, right? So summer review quiz corrections are due on Tuesday. If you guys need more correction papers, you can do 1A, 1B in one box. There are papers in the back table. I got tons more copied off. If you do need more correction papers, they're back there. So that's the homework this weekend. And starting section 1.4. Freakouts on 1.5. Sorry. Starting 1.4, but definitely not finishing. All right, cool kids.